In this problem, we're asked to find the work done when a mass is displaced some distance a from its equilibrium position. To solve this problem, we need to use the work-energy theorem and know how to calculate the work done by a conservative force. One thing to note before starting this problem is that we previously found the spring constants for these two springs to be 10 newtons per meter squared and 20 newtons per meter squared respectively, and we found that we can combine these two springs into an effective spring with a spring constant of 30 newtons per meter squared. We first apply the work-energy theorem, which states that the net work done is equal to the change in kinetic energy. The change in kinetic energy of the spring when it's displaced is equal to 0 because we both start and stop from rest. So the spring and mass are initially stationary before we pull them from the equilibrium position and are stationary right before we release the spring and start the oscillation. The net work is a combination of the work done by you when you pull the mass and the work done by the spring. Rearranging this equation, we see that the work done by you is equal to the negative of the work done by the spring. The spring force is a conservative force, so we can write the work done by it as negative the change in the potential energy of the spring. The potential energy of the spring can be written as 1/2 times the effective spring constant times the amplitude or the distance we pull the mass squared. Now we have an expression for the work done by the spring. We can now substitute that expression into our equation for the work done by U and evaluate to find that you do 37.45 joules of work when you displace the mass.